right, so I know Michael sounded surprised by my title, and that's because I think the title I gave him was different than this talk. I'm excited to share with you some results that we just posted a week ago, and I think they fit well with the theme of this conference, and can help illustrate some of the things that we're just beginning to be able to do in these kinds of systems. But before that, good morning everyone, and I want to appreciate you all for joining me at this 9,547 feet of elevation, which I'm very happy the organizers chose. It's really an incredible place and venue, so thank you very much. I'm quite literally out of breath. So, anyone else feeling this like real here? All right. So, if you are really interested in the other topic I would have spoken about, which is a more general topic on how do you do quantum simulation, or really any quantum circuit, in order to get noise-free expectation values at scale, and to also learn the full device noise map in the context aware way, you can check out the slides and video posted on my website here. But that's about all I'll say about probabilistic error cancellation today. Let's take a big step back and just get everyone on the same page. Okay? Quantum dynamics of interacting many-body systems are key to both fundamental and technological questions, and of course keep presenting us with surprises. Simulating and understanding these systems, however, is both challenging and sometimes difficult to understand what they're doing. However, as you know, by discovering symmetries, conservation laws, or even integrability in these systems, one can begin to simplify, to decode the complexity, and to unravel a little bit more of the mystery of these systems. Unfortunately, this task of finding such conserved laws or integrability is inherently challenging, and even proving the existence of such quantities is oftentimes shown to be an undecidable and tractable problem. To make things a little bit more concrete, imagine you have a spin system on some lattice that's undergoing dynamics under a unitary U, some time propagator. For the system, an integral of motion is this thing I'll call L here. That's an operator that commutes both with the Hamiltonian and with the time propagator, or the unitary itself. Simply put, this means that the integral of motion L maintains a constant expectation value that's invariant under time evolution. Now, as an operator, L can always be decomposed over the Pauli basis, which has an exponential number of terms. So this may not always be useful. For example, just to make this very concrete, imagine you have a toy model where you have a Hamiltonian that comprises one and two body Z operator terms, as shown here. To find an integral of motion, we can quickly observe that an operator Z, say on site 0, commutes with the Hamiltonian. The operator Z on site 1 commutes with the Hamiltonian, so and so on. Effectively, we conserve the local Z spin polarization. Now, in this case, we've just found an extensive number of integrals of motion. We can write down at least n of them. And their eigenvalues and eigenvectors can help us give a complete description of the entire eigenspectrum of the system, of all the eigenstates in this particular case. Now, for this trivial model, you could just look at the Hamiltonian and guess these, and that works. But if we try to do this more generally, this is very hard and even intractable. To make things a little bit simpler, let's look for integrals of motion, or ask the question, can we find integrals of motion that are local in some sense? So here I tried to paint a picture of an operator distributed over a bounded local neighborhood in a space. We'll call this the local neighborhood around some site K, and this L sub K should obey these constraints here. We call such an integral of motion a local integral of motion, or a Leon. Now, the system may hide more than one such Leon, or local integral of motion. It may have many integrals of motion that are local. And in fact, if such a system is described by an extensive set of local integrals of motion, we can refer to the system as integral, quantum integral. There's some footnotes here because integrability in the quantum setting is a tricky thing to define. When do such leons occur? Well, one setting in which they tend to arise is when disorder is present in the system. And as a function of the disorder that is spatial, you might see more and more of these local integrals arise. In fact, many of you probably have heard of many-body localized systems or have done experiments on them, and at least a few of you here have participated in this. These many-body localized systems themselves are suspected to have an extensive set of local integrals of motion. And just so I get a little bit of clarity, can you raise your hand if you're familiar to some degree with many-body localized systems? Okay, we have most of the folks. Do you believe in many-body localization? Well, any brave souls want to raise their hand? I see at least one, two, a few. Okay, who does strictly not believe in many-body localization? Okay, so we have a few on either side, and the rest remain to see. So don't be shy. Well, the hypothesis here is that in the semial regime, the original Hamiltonian can be understood as subsum over these leons, with local integrals of motion, where the leons themselves interact, but effectively it gives us some kind of more tractable description of the problem. If you really want to know the details, and I think many of you here are experts, but for those who are newcomers, I was just here in Colorado a week ago at giving a lecture at this wonderful Boulder Summer School in Defense Center Physics. I think you've heard about it in the QSIM Summer School as well, so please refer to those notes as well. But maybe for us, I'll keep it very brief and say two things. One, there's a tremendous amount of work and experiments that are very interesting, made by folks in this audience. So I apologize that the font is a little small here, and I may have missed a few, but there's a lot of interest in the community. In our case, we're mostly just interested in saying that perhaps these systems, whether it's in a phase or a regime, not a straight phase, or whether it's a pre-thermal regime, may possess these local integrals of motion, and we'd like to see whether that's the case operationally. Of course, the existence of MVL is under debate, and what we then have to take a step back is to say, well, perhaps we don't need to find strict integrals of motion. We might be okay in also exploring to see if we find approximate or pre-thermal integrals of motion, meaning integrals of motion that almost commute with the time propagator. And what happens at exponentially long times, well, who knows? So this is still quite tricky, potentially, because it's beyond final ground states. We're interested in the time dynamics of the problem. So the scientific question I'd like to ask in this study is, can we use a quantum computer, a digital system, to uncover operationally these integrals of motion of a large, disordered many-body system? Before getting into all the details, let me start with a bit of a preview. Imagine some spin system of many interacting spins. We'd like to map it to a physical quantum processor. This is a superconducting quantum processor with its noise map from PEC mapped out. And this experiment I'll show you is going up to 124 qubits in this 2D heavy hex topology. We go up to about 60 layers of consecutive parallel C-naughts. That's about 20 Cloquet steps. I'll introduce that in a moment, or about 2,600 total C-naughts. One particular advantage we leverage here is that we can run many circuits. So we run about 1/3 circuits for the experiments, and about 500 million shots, which will be a resource we can use in order to trade runtime for accuracy. Since these devices are inherently noisy, but we can overcome that noise using error mitigation, which requires more runtime. So it's about 80 hours of runtime, and we did this whole thing through the cloud. Okay, here's the hardware map of this particular chip, which looks 2D in this heavy hex topology. Each circle is a qubit, and they have nearest neighbor interactions. We can program some initial spin state. So here, the spin, the color blue, means that the qubits are initialized in 1, or the spin is pointing up, let's say. The rest of the qubits are in ground state. And then we can run the time evolution of this interacting many-body quantum system in different regimes of the interactions. So you notice here on the left, At step 0, you can see a logo, and then as time goes on, that logo very quickly disappears. It looks like the information has quickly scrambled into high-rate observables. So this is probably in a thermalizing regime, whereas on the right-hand side here, the interaction strength disorder is different, and you see that the logo doesn't disappear right away. It looks like it's getting locally rescrambled. And underneath that, there might be hiding these neons, which we'd like to extract. Okay, let's get a little more concrete. What is the spin lattice we'd like to study? So imagine some interacting spins over some disorder. Each little circle here represents a spin. The time evolution of this model will be based on a flocate evolution. So time is discrete, and in each time step, we apply some global unitary use of f, and that will be our time propagator. Concretely, this use of f looks like this. Basically, it's a Ising model in some sense. We have a kinetic term that has interactions. Theta here is going to be a gate that has both x and z components, preceded by a CZ gate. These are always the same at each time step for each qubit. And we also have some spatial disorder, where at each site we're going to have a different phase that is constant in time, but different for different spatial sites. And this phases will be randomly sampled from -pi to pi uniformly, while we'll vary the angle theta here for interaction. Now there are two, let's say, potential regimes. In one regime, we start with information locally encoded on some site. And if the interaction dominates the disorder, let's say, then you might get this light cone of the information spreading and propagating out. That looks like the spread picture. Whereas if the disorder dominates, you might have localization of the information, and maybe it doesn't propagate out, or it does much more slowly. And underneath that, you might have local integer motion hiding, which can be understood as some combination of many polyterms of higher and higher weights. Now, to do this experiment, we have to overcome the noise on the quantum devices. And to do that, we employ a composite error mitigation strategy, which involves digital zero noise folding, polytwirling, dynamical decoupling, custom readout mitigation, modified M3, and then we combine all of these in different ways. We optimize things. You can ask me maybe the questions if you want to know more about that. So taking all of that together, let's start with just a benchmark. How well does the device do? How well does the model do? And we did a number of studies here: spin imbalance, classical numerics, one-particle density matrices, scaling with system size, so and so on. But in the interest of time, I'm just going to focus on the simplest one, and you can check out the paper for the rest. So here's a 104-qubit 1D chain snaked around this 2D IBM Washington and Cook device. To test the memory in the system, to see if there is some memory of the initial state in a local way, we can prepare an anti-ferromagnetic type of pattern. So each qubit is prepared in either 0 or 1, alternating as shown by the colors here. And we evolve the system under a fixed disorder realization for different interaction strengths. From other numerics, in 1D, we can say that there's a critical angle somewhere around 0.16 pi for the interaction strength. On one side, one should be in the ergodic thermalizing regime. On the other side, one is probably in a 1D FBO regime. So here's what the spin density evolution of the qubits around the middle look like. I could show you all of them, but it's just too much information, so let's zoom in. If the interaction is weak, we start in this anti-ferromagnetic pattern, and you notice that it more or less stays visible as a function of the Fouquet cycle. However, if the interaction is stronger, we see that the pattern quickly dissipates. To get more quantitative, we can look at a traditional type of charge imbalance, or in this case it's a spin imbalance, which looks at how many spins should have been up versus how many spins should have been down, normalized to 1. And you notice that in the ergodic regime, the spin imbalance is a signature of the memory in the system, decays very, very quickly. Whereas in the other regime, we see this much more slow decay of the memory. And in fact, it's a little noisy, but if you're careful, you can see that it tends to plateau to some fixed parameter here. Okay, so that's our benchmark and sort of setting for the stage. Where things get a little bit more interesting is now, let's see, how do we, from this data, uncover the actual integrals of motion? So the basic idea is the following. Consider some spin chain. You can measure different Pauli expectation values that time evolve, and you can measure more and more of them. Let's say that these are all local in a sense like this. In fact, you can keep measuring and parallelize things, and you get what looks like basically a bunch of chaos, pure anarchy. But if you look through these in the right way, then you can see that, then perhaps you can find that a certain linear combination of these Pauli expectation values in time is going to be a constant. So it looks like a conserved quantity. Now, it may be a conserved quantity with respect to the initial state, not a true conserved quantity. So you have to also look at different initial states to make sure that this combination effectively is fixed for all time. It's actually a little tricky to do this the right way numerically. We've tried a number of techniques. I won't walk you through exactly what we did, but I'll mention it's based on these beautiful papers. And I know a few of you in the audience are working on very cool similar ideas, so I'd love to talk over lunch. But essentially, you look at some time-averaged operator that's propagated from some initial site. You can ask me the questions if you want. Here's what the experimental data looks like. So we measure a number of these Pauli expectation values, such as shown here. Because there's so many curves, you see a sort of scramble of orange and white. And if we look for an integral of motion, just like we introduced earlier, we can actually find, by churning, let's say, this post-processing of the data, you can find this blue curve here. So those blue dots represent experimentally extracted near conserved quantity from the quantum computer that's eradicated. And it's conserved in the sense that it looks like it's flat for different initial states and also for this particular time evolution. Of course, it's not perfect because we have finite time, finite size, and also some error in the experiment. But because this is a 1D system, we can take the exact system, cut it from qubits 44 to 56, and we can do the classical numerics. And in fact, we do the classical numerics, we find that the Leon value should have been 0.5 in this particular case for this particular disorder realization. And in fact, we do get something pretty close to that experimentally. The way you can kind of look at this operator, because this curve is again representing an operator, is that this Leon is mostly dominated by a local Z term. It also has the X term. It has a 3-body ZCZ interaction. Then there's some ZYs and so on. Now I've shown just the Leon in the center, which is located on qubit 50 in this linear chain. And here I'd like to plot some kind of representation of the density of the operator over the sites, because I'd like to see that it's spatially localized. And not only spatially localized, but it's also localized in the Pauli space. So as you look at the total Leon, it's broken down by components that have different Pauli weights. So here are all the Pauli weight 1 terms, which are mostly centered. You see that there are 2-body terms, which here are shown in this curve. And then as you go to higher and higher Pauli weights, you get this localization in that your dominant Pauli weight as well as this real space. Now, we can do this in parallel for more qubits. So here's basically qubit 0, 24, 50, so on and so on. And we can do this in parallel and find an extensive number here, 104 different local integrals of motion in the 1D spin chain. This graph provides you with reconstruction of the operator amplitudes. Because there's so many Leons and they overlap, I've just plotted them on different axes. So the first one shows you the 0th, the 4th, the 8th Leon. The next one shows you the 1st, the 5th, and so on. And so this is now really looking at these approximate reconstructed Leons for a particular disorder. that looks like we have a complete and extensive set. And you can, of course, look by their operator weight, and you kind of decompose them both in space and in operator space. But maybe it's more interesting to look at how does this now compare to classical simulations, so we can validate the quality of the data extracted from the quantum device. Okay, so to do that, let's look at the average Leon and the bulk. And this is a comparison where the data you saw is just plotted with the dots, and we've done the classical numerics across the device, the truncating, and that's shown with the solid lines. And we see that both for the total weight as well as the individual contributions from different poly weights here, we have pretty good agreement, especially near the center of the Leon. From this, we can define an error metric that's basically how well does this Leon commute with the Hamiltonian, so how flat is it in space. And we see that for most of the local integrals motion we extract, the error is quite small. And then occasionally we see regions where the error tends to be pretty bad for a number of them. And this we attribute to a couple of really bad qubits that we couldn't avoid because we're using the entire quantum device. So at least we know what's causing the error there, but most of them seem to do pretty well. So that's 1D. That's kind of nice, but it's maybe even more interesting to look at 2D. Now in 2D we repeated all of the benchmarks, basically everything we saw in 1D, so I'll try to cut to the point here, but we see all the same spin imbalance. We do the one particle density matrix spectrum, we look at the closing of the gap, we do system scaling as a function of how many hexagons are in the system. There's some interesting questions about MBL or not there. But in this case, we have 3 seconds per layer. The interaction graph is colored. And we can compare different initial antiferromagnetic states. Just like you saw the spin imbalance in 1D, here we have the spin imbalance in 2D. Precisely at the interaction angle theta 0, the circuit is integrable. It's a Clifford circuit, so we know exactly what the value should be. There should be no interactions, so it should be always 1. With error mitigation, we get pretty close to that. You notice, yeah, the error's there, but it was good enough for what we cared about. And then as you turn up the interaction angle, you see that the thermalization seems to happen faster and faster and faster. Now, to show you the Leons in 2D, it gets a little more tricky. Here, really, I should call them pre-thermal Leons, most likely, or approximate Leons. There are 2 types of distinct topologies for these, both for vertices or spins that are coupled to 2 neighbors, or spins that are coupled to 3 neighbors. And we can extract sort of the detailed portrait, if you want, of the Leons, and do that as a function of the poly weight that goes to higher weights. It's interesting because in 1D we saw a clear localization in both operator space and in real space, whereas in the 2D case, the localization in operator space is not as clear. You notice how some of the terms here for poly weight 3 might be bigger than those for poly weight 2. And this is probably a signature of some of the underlying dynamics here that maybe these are just pre-thermal Leons. So maybe to summarize briefly some of the idea, I think I got kind of excited about this project because I think we're looking at some interesting and cool physics. I should mention in the 2D case, I couldn't show you the comparison against classical numerics because me and my colleagues couldn't figure out how to do it. It's beyond our ability to simulate that system because the information goes pretty quickly. I'm sure one of you in this room can do it and probably tell us how well we did. But we're getting a little bit closer and closer to this region where we can start to do circuits that are both at scale of 100 qubits plus and at a deep depth of 100 layers of parallel gates deep, where I think we'll find more and more interesting problems to look at and do. And of course, there are many ideas. I'd like to thank the team a lot. Derek is here, so you can ask him and me for questions. We have 2 wonderful interns on this project. And if you want to know more, check out this poster at the QSIM poster session. So, thank you. We'll take any questions there.
Yes, yeah. If you can come up.
Great, thank you for the really interesting talk. I guess one thing I was wondering is, with this question of, are these conserved quantities or are they nearly conserved quantities? What are the prospects for actually answering that question with a quantum device? I imagine the noise and the sort of finite precision of measurements might make it quite difficult.
Yeah, great question. I think even if you had no noise, I think it's still a very, very difficult question. Probably somebody in the room has an even stronger answer than I do. Actually, you right there would know a lot. But there is a theorem on undecidability of some of these questions because you know, if you use these kinds of methods where you look at some time dynamics, you can really you have a horizon. And you know, the best we can say here is that these are approximate local integrals of motion, basically local integrals of motion with the time scale of observation. You know, what happens at exponentially long times, I have no idea. But I get some comfort from sort of thinking of Deborah's number from like hydrodynamics, where you talk about the scale of observation relative to the scale of the phenomena. But probably the best we can say, maybe somebody has more to say here, is that you know we can give a bound at some level, but beyond that, I'm not sure.
Okay, thank you.
Go ahead. Yeah, please, more.
Yeah. My question was about how you were forming the local integrals of motion from the dynamics. You briefly showed a slide using time averaging, and I guess maybe the question I was wondering is, are you solving an optimization problem to find the best conserved operators, or is it merely, an operator that you're taking some starting operator and averaging over time, or some combination of both?
Yeah, that's a great question. So basically we tried both things, and I think this one seems to work the best, where you start with an initial guess, right? If you start with, let's say, a Z operator, you take some guess, Z operator on some site, and then you time evolve it, and you average the time evolution, that will naturally generate an integral of motion if you go over infinite time. So that's kind of the basic premise of these protocols described here, and if you go to Derek's poster, I'm sure you can sort of go into details. But we did look at different post-processing numerical schemes, variation of one, schemes like this, and this one seemed to work the best in practice. So there were a couple different things we tried. Great, thanks.
Hi, thank you for the wonderful talk. I wanted to ask about the statistical uncertainties that rise due to the quantum error mitigation part, and would that uncertainty be small enough so that you can actually distinguish whether it's a Leon or not?
Yeah, that's a great question. So, as you get to, you notice that way I should point out, this is a logarithmic scale, so we're getting to pretty small values here. So I think for values up in the order of 0.1, 0.05, we feel pretty confident. There are two questions, right? There's statistical uncertainty and there's bias. The method we use here, strictly speaking, is not an unbiased estimator in any sense. It's sort of a good enough method, and it's very efficient and fast. If I had to do this experiment again, I would probably use a combination of probabilistic error cancellation, which is the technique I mentioned on the very first slide, which guarantees you an unbiased estimator, up to some learning fidelity. And there's sort of very strict, rigorous gold standard bounds. I'm sure I'm talking time inequalities to tell you exactly what you should expect for the error mitigation. Here we can compare both from the small-scale experiments and from self-consistency what the error is. And you notice that the errors here we managed to get were pretty small for most of them, but some of them were a little big. And the error mitigation here probably does way better than you would get without that. But it's still not able to overcome the really strong ones here. I think we know what to do to get past that and to move to the sort of 100 qubit plus level. I think that's a combination of even more techniques. Composability here becomes really key. So there's a trade-off between runtime and accuracy. So if you really want to guarantee that, basically we can turn up the runtime. We can use an even more accurate technique. But here we thought it's a good compromise to use a pretty good technique that has some sort of balance, but isn't rigorously guaranteed. So I would say there's a needle that you can thread between the two.
Thank you so much.
Yeah, so I have a related question just on the scalability.
You're allowed to ask questions?
I am allowed. So, yeah, I'm just just a high level question, like how much data was going on in this experiment? Like, was this really scalable? I mean, it looked like it had been on, my laptop.
Yeah, well, to give you a sense of, I guess, the quantum runtime, if you want, it was about 80 hours of quantum runtime. We took about 350,000 different quantum circuits with some number of shots. Now, these circuits include twirling instances, they include stretching factor instances, so there's some overhead there in terms of that. And then there's also the number of shots you took. So we've, for the whole, this by the way, for the whole paper, for all the data I've shown you. I'm not sure that, how does it scale?
How much data
Yeah.
does this represent in gigabytes?
Gigabytes, okay. Derek, do you have a number in gigabytes?
I mean, the shots aren't that hard to store, tens or hundreds of gigabytes. The real problem is you have 350,000 circuits that each are several megabytes, but that's aside from the client computational problem.
Yeah, so it's not too bad, it's doable. And the protocol scales. Now, it's harder in the locality. It's probably exponential to the locality unless you subsample. But in terms of the number of qubits, it's all parallel. So it's linear cost, and that's constant cost, I think, in that sense. So in the sense of scaling to more qubits, the protocol is scalable. And scaling to, what we would have done actually, I guess we had a little more time for the experiment, is gone closer to the potential phase transition and looked at increasing complicated leons to get closer to the transition from their MPL-like regime to an ergodic regime. Localization length would increase, so we'd have to maybe sample a little more. But also it'd be harder to simulate classically. Maybe that's an interesting playground to play.
Yeah, very fascinating. So yeah, I think we're out of time, so let's thank the speaker again.